Okay, so this is Calc 2 in Lecture 1. Let me review integration by substitution, which should have been in Calc 1, but anyway, I usually start with this. So integration by substitution, this is in fact case 1 that we have. So let's write here case 1. And those are integrals that look like this. We have g prime f of gx dx. So the integrand has an inside function. So there's a function outside this f and an inside function, and you can recognize the derivative of the inside function outside of this. Well, it's not always the exact derivative, it might be a multiple of that, so, but you can recognize because I hope that you know differentiation enough to recognize that. So, if this happens, and by the chain rule, if we have a function, capital Fx, such that f prime x is this fx, then by the chain rule, the derivative of this is f prime gx times g prime x. And since this is f, so the derivative of this is that. Therefore, we can write this as, so this is in fact the integral of this thing, f of gx prime dx, and integral and derivative are like inverse to each other. In fact, this is not integral, this is what we call antiderivative. So antiderivative, derivative are inverse, so we will get f of gx plus a constant. Don't forget the constant. Okay. So, when we see an integral, that's what I do. I usually try integration by substitution unless I immediately can recognize that as integration by something else or some other method. But if I have no clue, then, and if I can see that there is an inside function, then I say, okay, well, maybe this is integration by substitution. And I try integration by substitution. If it works, it works. If it doesn't work, then I will try something else. Okay, so what are some, first of all, this one can be like this. So this one doesn't have to be like this. As I said, it can be a multiple of that. So it might be some constant times g prime x, f of gx dx. So this constant just remains. So this will be f a times f of gx. That's a constant. Okay, so that's what I said, that this outside, this is an outside function, this is the derivative of the inside function. So if you don't see the exact derivative, you might see a constant times the derivative. So let me write some examples here. I wrote some examples. So this can be, it can be this thing, 2x radical x squared plus say 4. So the inside function is this. This is exactly gx, and this is exactly g prime x. And 2, I let's write this like this, x, the same thing, x squared plus 4 underneath. Then I can see that the same gx is here. So this is the gx. What is this? This is not 2x, this is in fact 1/2 2x. So that's 1/2 g prime x. And this 1/2 is in fact that constant a, which I so that's another one. Well, I can number 3, which you will see these type exclusively in another section, but let me write it here. So number 3, which you will see, as I said, in another section, it can be cosine x, sine x, dx, and you can see a function and its derivative here. The function, in fact, is this, and this is g prime x. Okay? And now, let's identify in each case that fx, or what sometimes they call it the outside function. So let's identify for each one of them the outside one. So number 1, fx is what? Fx here is, you can see it's obvious, that is, inside function is inside the fx. So in this case that is square root of x. And gx is x squared plus 4. Number 2, what is it? This thing is gx. Well, usually you can find gx easily. But then it is 1 over x, right? The fx is 1 over x. And the gx is again x squared plus 4. Number 3, well, you know what gx is again. Finding gx is not that hard. Well, what is fx? Well, f of gx is sine x. So what is it? And the gx is sine x itself. So fx is in fact the simplest function, x itself. So gx is sine x. But in each case, if we use that formula I gave you, you can find the integral. But usually this outside function is not easy to see, especially immediately. So there is a method. I mean, there's a way to do it without trying to find that or trying to identify that fx. So let me show you how to do that. So let me erase these. While we solve them, don't worry, these are examples that should be solved anyway. So it was just how to identify. In fact, in integration, that identifying which method should be used is the most crucial part. Okay, so let's go back to the example in the general form. So I had a times g prime x, some function f of gx dx. Now what we do here we call substitution. In fact, substitution, you might say, well, what is the substitution? This is in fact this. So one, what you do is you let u be the gx, 2, then du dx is g prime x, and 3 du, but you see this du dx is it means the derivative of u with respect to x. It can also be treated as a fraction, so you can cross multiply. So du times 1, this times this, so that is g prime x dx. Okay, so we substitute in the original one. What do we substitute? We substitute this and this. So this will become integral a g prime x dx is the du, so let me write it here. And this is f of u. Okay, so it is the a comes out, integral f u du. And that is in fact a, remember, f of u plus a constant, where f prime is f. Okay, so that is what happens. So this, say, process is what we call substitution. So we substitute u for gx. No, it doesn't have to be u, just we can choose anything, v, w, whatever. Now sometimes students prefer to do this. When they find this, so they in fact don't see this over there. So they say, okay, well, let's find dx from here. So I write it as 3 prime, which means this is the same thing, but so you write dx equals, well, let me see, no, we cannot see that red one here, so let me use another color. dx, oh no, 3 prime, so you find dx from here, so dx will be du over g prime x. Now you substitute this one and this one. So either this and this, or this and this. So the first one is definitely u equals gx. The second one, if you can identify this, if you can find g prime x dx, then just throw it away and put du for that. Otherwise, if you can see it, you can just write du over g prime x for dx, and then the g prime itself is cancelled. Especially if this works nicely if you cannot really see the derivative, you cannot see that there is an a times the derivative. Okay, so let's go back to those examples and use this procedure to find them. Example 1 was, I guess I can remember that. That was 2x, x squared plus 4 dx. So, well, that was the procedure or the algorithm was, say, u is the inside function, 2 du dx is simply 2x, and 3 dx is du over 2x. So I used that third one, I mean the half one, say. Now we substitute here these two. So I have 2x radical u times du over 2x. So the 2x and 2x cancel out, and I will get u to power 1/2 du. And always, when you have square root, radical, or whatever you have, write it as an exponent. Don't write radical u. And I prefer to say radical. Sometimes I use square root, but that is in fact something else. So, now what is it? By simple integration of polynomials, you know that this is in fact 1 over 1 plus this exponent, 1/2 u to power 1 plus 1/2 plus a constant. So to simplify this will be 2/3 u to power 3/2 plus a constant. And don't forget to substitute back for u. So the result is 2/3 times x squared plus 4 to the power 3/2 plus c. Okay. So let me double check. Well, substitute for x squared plus 4, then the u dx is this, then find dx in terms of the rest of things, and that is d over 2x, and substitute for this one and this one. So we are substituting for this and this, right? So we'll so we are substituting over these two, in fact. Okay. Okay, so x squared plus 4 is u, and dx is du over 2x, and that's over there. And now we get radical u. Radical u is u to the power 1/2, and the integral of u to the power n is 1 over 1 plus n, u to the power 1 plus n, if n is not negative 1. Okay, and simplifying that, that gives me this end result. Now, the other one was, number 2 was this thing. X over x squared plus 4 dx. And let me erase everything. Well, it's the same thing, right? At this here, no, that's not the same integral, but here I have the same substitution. So let's plug in. I have x here, I have u here, and then I have du over 2x. So the x and the 2x cancel out. I have integral. There is a 1/2 here. 1 over u du, right? So 1/2, this 1/2 comes from here. So when you cancel this x and x, you will get 1 over 2. So that is in fact 1/2. 1 over u du is ln of absolute value of u plus c. So I will get 1/2 ln of absolute value of u. U is x squared plus 4. It's never negative, so I can just remove absolute value, and x squared plus 4 plus c. Well, you might say this, that was also 1 over u, that's u to the power -1. Yes, remember, recall, let me write this. Integral of u to the power n dx of du, let's say. Du is in fact 1 over 1 plus n, u over 1 plus n plus c if n is not -1, and it is ln of absolute value of u plus c if n is -1. So that was this second case. You see 1 over u is u to the power -1. So when you see 1 over u, that is ln of absolute value of u, and don't forget the absolute value, because that expression might be negative. So, and it shouldn't be 0 or negative. It should be positive. Okay. Now the third one was, let me erase everything here. So the third one was, if I remember correctly, number 3 was integral of cosine x sine x dx, and so let me erase everything here, that's something different. Okay, well, you recognize that this is the gx in fact and the g prime x exactly. So well, let's see. So I have let u be sine x, then du dx is cosine x, and then the x is simply du over cosine x. Let's substitute this one and this one for these two, and we have this is cosine. Let me see. So I have cosine x. I didn't substitute for this times u times dx over cosine x, which is integral du. So integral u du. So that's 1/2 u squared plus c. So that's 1/2 sine squared x plus c. Okay, so that is the end result for the third one. Now, as I said, this is in fact trig integrals, trigonometric integrals, which is one of those integration techniques which comes next. But for now, we need this for the next chapter, in fact, chapter 6. So, 3 interesting examples. Now, I can give you some general formulas for some of them, say. So, especially the one that is used extensively. So, special case is this. Special case is if I have f prime here, let me see. Let's write g prime. G prime x over gx dx, right? So if I let u be gx, then 2 du dx is g prime x, 3 dx is du over g prime x. So this becomes a integral g prime x over u times du over g prime x, which is integral of 1 over u du, which is ln of u plus c, which is ln of absolute gx plus c. Okay? So this special case helps us to find integral of tangent of x. In fact, one of those examples was an example of this one. I guess the number 2 was an example of this one. And remember, I can have a constant times this. So there might be a constant times this, so this a comes out. So I will have an a. So it doesn't have to be exactly g prime x, it can be a, so constant times g prime x. Okay. Now, an important example is tangent. So integral of tan x dx. Well, you might say, gee, I don't see any outside function or inside function, anything. Yes, but tan x is what? Tan x is in fact integral sine x over cosine x dx. Now what is this? This is like the gx, and this is minus g prime x. Right? So that is gx, and remember the derivative of cosine is minus sine x. So sine x is minus derivative of cosine x. So this minus is like minus 1, so that's in fact that constant a. So by that special case, I have minus, the minus comes out, ln of absolute value of cosine x plus constant. I prefer this one. Some people just bring this negative inside and write it as ln of secant of x. Well, I can do that. But I prefer this one. So if you write it as ln of cosine x to power negative 1 plus c, then that is ln of 1 over secant, so it's in fact secant itself. 1 over cosine x plus c, and that is there's a minus here. So minus L, oh no. Oh yeah, I put the minus over there, so the minus comes here. So that is ln of secant x plus c. Now, if you cannot remember, let me write some rules on ln. So I have ln of ab is ln a plus ln b, ln of a over b is ln a minus ln b, and say some k, ln a is ln a to power k. Okay, so that's what I used here. This k here is negative 1. And here is this k. Oh. Sometimes they play a trick on you. So, interesting example. This one is in fact nothing. Well, we can say it well, but interesting example. That is this 1 over 1 plus e to power negative x dx. You look at this thing and say, gee, I can't see derivative of the, I can see an inside function, but the derivative of this inside function is e to 1 minus x. Where is it? No, you can't see it. But let's do this. Let's multiply both numerator and denominator by e to power x. E to power x is never 0, so I can do that. That doesn't change anything. So this will be integral e to the power x times 1 plus e to the power negative x dx, and that is e to the power x, then in this time this is e to the power x plus 1 dx. Okay, now you can see the u or the substitute. So this is the inside function. If u is e to the power x plus 1, then du dx is e to the power x itself, and 3 dx is du over e to the power x. If I substitute, I will get integral 1 over u du. In fact, I could have used that special case. This is u and this is du, right? This is gx, g prime x. So that's ln. So this is in fact ln of u plus c, and this is always positive, so this is ln of e to the power x plus 1 plus c. I don't need the absolute value, so I just put parentheses here. That's always positive. So, it could have been 1 minus e to the power minus x. So, that's also something similar to this. Okay, so whenever you see e to the power minus x, one trick is maybe if you multiply by e to the power x, if it is in the numerator or denominator or whatever, maybe it helps. I'm not saying it always helps. There is no general rule for that. But sometimes the e to the power negative x, when you multiply it by e to the power x, you will get 1, because that's e to the power 0, which is 1. That's why I had 1 here. So that's e to the power x minus x, which is e to the power 0, that is 1. So this is the first case that we use something that we call substitution. And this is like the reverse process of integration, chain rule, differentiation using the chain rule. So it's the inverse of the chain rule. Okay, now, case 2. Case 2, I will start with an example, in fact. So case 2 is examples. Well, let's see, maybe I just have one example in mind. You might see something like this: x plus 3, the root of, say, x plus 5 dx, something like that. And you look at this and see an inside function, x plus 5. And but you don't see that its derivative on the outside. So the derivative of this is 1. But it's not 1. There is no 1 here if it's x plus 3. So that's what we do. Even if you start with substitution, you probably go somewhere, but not exactly. So if you start with substitution, which is correct, in fact, we should use substitution. So let u be x plus 5. Then you say, okay, du dx, I know that. Dx is 1. So this gives me that dx equals du. X equals du. Then you get stuck. It's okay, but what happens to this? Yeah, that's what happens. So that's what happens. So we find x in terms of u. So find x in terms of u. Find x in terms of u. Substitute for x. In fact, we can substitute in both of them, but one of them is definitely u. So from here I have x is u minus 5. Okay, so now we have, so this becomes u minus 5 plus 3 radical u du, right? So that is integral u radical u du minus 2 integral u du, right? Minus 5 plus 3 is minus 2. Then this one is u to the power 1/2 times this, that is u to the power 3/2 du minus 2 integral u to the power 1/2 d. Now these are two simple integrals. It's like integrating a polynomial. So let me erase this and find these two integrals here for you. So that is 1 over 1 plus 3/2 u 1 plus 3/2 minus 2 1 over 1 plus 1/2 1 plus 1/2 plus a constant. So this is 2 over 5 u to the power 5 over 2. In fact, this the reciprocal of this thing, minus 2 times 2, that is 4 over 3 u to power 3 halves plus c. So the end result will be 2/5 x plus 5 to the power of 5 over 2 minus 4/3 x plus 5 3 halves plus c. So that is the second type, let's say, or the second case that you can use substitution, and there's no general rule like the other one. You have to just look at the integral and see that it is a substitution. Now, let me give you another example, which this one can be solved using another integration method called integration by parts, but well, I might give you an example of this one when I do integration by parts in the coming lectures, but for now you can solve it using integration by substitution. So let me give you another example of this type. Example 2 of this type is, well, let's write the same, plus 6 times x minus 3 to the power 12. Well, you might be intimidated to expand x minus 3 to the power 12. So let me give you that expansion, because it is a good review at this point. We might need that at some point. So what is that binomial expansion? Binomial means 2. So if I have, say, a plus b to some power n, then this is my what? This is a sigma, in fact. And j, or let's write k from 0 to n. N choose k, say a to the power k, b to the power n minus k. Okay, so let's write some of them. A plus b to the power 1 is a plus b. 2, a plus b to the power 2 is a squared plus 2ab plus b squared. 3, a plus b to the power 3 will be a 3, 3a squared b plus 3ab squared plus b 3, and so on. Okay. So at 12, let's see. So this raised to power 2 gives me 3 terms, to the power 3, 4 terms. So this should give me 13 terms. 13 terms, if I find them correctly, times x, that is 1, 13, and times 6, that's another 13, so I have 26 terms to integrate. And I have a negative here, and I should be careful about the negative, because if I have a negative here, then this will be what? Say, for example, this one, a plus minus b, then I should be careful. I have a squared plus 2a times minus b plus minus b squared. So I have to be careful. Like in this case, this middle one will be minus 2ab, but this one will be b squared. So it's not worth it. Don't expand. In fact, I could have given you 120 rather than 12. Then there was no chance. So that is in fact a substitution. So what? You can recognize that is the inside one, x minus 3, 2, du equals dx, and 3. It's not always du equals dx, right? So it might have 2x plus. Well, let's do that, right? So let's write 2x. It's better. So then I have du is 2dx, and this gives me dx is 1/2 du. Okay, so this third one will be solve for u. So I have u equals 2x minus 3, so this gives me x is 1/2 of u plus 3. So this will be integral 1/2 times u plus 3 plus 6 times u to the power 12 d times 1/2 du. Right. So let me simplify. I have 1/2, so that is 1/4. Let's put it outside. Then I have u plus 3 plus 12, so that is u plus 15, I guess, right? So I have u plus 3 plus 2 times 6, 12, 15, times u to the power 12 du. So that is 1/4 integral u to the power 13 plus 15 u to the power 12 du. So that is 1/4 1 plus 13 u 1 plus 13 plus 15 over 1 plus 12 u 1 plus 12 plus c. So that is 1/4 and 1/14 u to the power 14 plus 15 over 13 u to the power 13. I can write this here outside. So let me double check. So 2x minus 3 is u, and du is 2dx. So I have a 1/2 du, then u is 2x minus 3. So 2x is u plus 3 du. Okay, then I have 1/2 u plus 3 plus 6, that is u plus 3 plus 12. 15, I have 1/2, that's 1/4, and u to the power 12. So I have u 13 and u 12, and that's 15 over there. And so the first one is 1/14 u to the power 14. The second one is 15 over times 1/13 u to the power 13. Then substitute, and then this gives me 1/4 times 2x minus 3. Oops. Like that. 1/14. Okay. So that is the other case. Sometimes if I have, for example, x plus 6 to the power 2, for example, here, I can still do that. But if I have something else, if I have like 120 here and say 65 here, then no, that is not easy to do. But this one, when one of them, you have two expressions, both of them have degree 1, so they're like linear terms, ax plus b, like that. And one of them is raised to some just big power, say, and it's not worth expanding it using the binomial theorem. The other one has a lower exponent. So I can even go up to 4, for example. If I have x plus 6 to the power 4 and the other one is 12, I can still do that because x to the power 4 is not that much. That's like 5 terms. But anyway, it's just you just use your say experience in solving integrals like this. Now, finding derivatives, as I have always said and I say it here, finding derivatives is not that hard. I mean, you can find derivative of almost every function if it's a nice function, but finding integrals is not that easy. In fact, it's like more than just, it's not, I can say it's science or something, it's mathematics. It's kind of like an art. So you have to have enough experience in doing it. So if you have done enough integration, then when you see an integrand, an integral, you immediately can say, boom, that's it. Now, one last thing which I would like to discuss is, in fact, this. If this is if I have, say, limits for the integral. Okay. So say I have this thing and it goes from, say, 0 to 1. Let's just put 0 to 1. Then I found this. So I found that is in fact 1 over 4 u to the power 13 plus 15 u to the power 12 d. And I had u equals 2x minus 3, right? So I can go up to this point, then insert 0 and 1. I can stop here and change the limits of the integral. Use this. So I say x 0, x 1. If x is 0, that gives me u is minus 3. X 1 gives me u is minus 1. Right? So minus 3 and minus 1. So this will be minus 3 minus 1. You don't have to go up to the end. You can just do it here. But be careful. Some students simply write 0 and 1 again. If you are changing, if you are using integration by substitution and you are not going back to the original form and you want to just plug in numbers here, be careful. You have to change these two according to this formula. Okay? So in this situation, if it is minus 3 to minus 1, then this was 1/4. 1 over 14 u to the power 14 plus 15 over 13 u to the power 13. There's no need for the constant here. Minus 3 minus 1. Just put minus 1, find it, and then minus 3, and you have the result. There's no need to go back to the original form, which is this, and plug in 0 and 1. It's the same thing. So I think I have given you enough. So you know integration by substitution, and most often the first one happens, which is when you see an inside function. So in any case, if you see an inside function, you should think of substitution. Or let's say when you see an inside function and its derivative, or a constant times its derivative, then you should think of substitution. I'm not saying you cannot solve it using other methods, but maybe the other method is easier, but well, if you can do it using substitution, then do it. Why should you use anything else? Unless that is way easier than this. Okay, so that was some review from Calc 1, and next time I will start some applications of integration. Okay, so see you next time.